Hello, students. I know we didn't quite get a chance to finish everything up in class today, so I want to talk about some important ideas here with enthalpy and entropy as we're talking about forming a solution. So the diagram that you're looking at right now is showing the delta H for different processes that are happening. We talked about how we have to separate the solvent particles from each other, so we're going to be breaking some intermolecular forces between water molecules, and that's represented by this change in enthalpy here. We also talked about how we have to break apart the ionic bonds holding the salt ions together in the crystal. So we have a delta H that's associated with those ionic bonds. Notice in both of these cases, we're breaking the bond or the interaction, and that requires energy. We have to add energy in. Those are endothermic processes. Anytime we're breaking something apart, breaking the bond, that's going to be endothermic or require energy. And then on the other side, we're going to be forming these ion dipole forces. So this diagram sort of shows these layers of water molecules surrounding our positive and negative ions. And those are making ion dipole forces. And in this case, our ion dipole forces are slightly smaller than the overall energy that we need here to break apart the hydrogen bonds and the ionic bonds. But because we're forming these multiple layers, it turns out there's a lot of ion dipole forces. The overall magnitude here is pretty big for those ion dipole forces. And because we're forming those interactions, that's going to be exothermic or release energy. And that's true generally. Anytime you're breaking a bond, it requires energy. Anytime you're forming a bond, it releases energy. And overall, now if we want to add all these things together, breaking the hydrogen bonds, breaking the ionic bonds, forming the ion dipole forces, we end up here with an overall delta H for this process of solution formation that's slightly positive. Now, how this is going to work out in practice depends on the magnitude here, the strength of the ionic bonds, and also the magnitude here for those ion dipole forces. And it turns out if you have larger charges, like a +2 or a +3 ion, that tends to make this more extreme. The ion dipole forces will have to be bigger because it takes more water molecules to sort of stabilize that positive charge. This diagram is based on Hess's law, which you may remember from Chem 105 because enthalpy is a state function. So if we want to know how to go from just our solute and solvent to our solution, we can actually go through the three separate processes, follow a different path around this way to get to our final product over here. Or we can also just go from our water to our solution, and this little arrow here is the sum of all of these three arrows here. Because we're starting and ending at the same place, the path doesn't matter. So that's why we're able to look at this way. Now, some salts are going to have a negative delta H of solution, and some salts are going to have a positive delta H of solution. And it depends which salt we're talking about. So for example, a typical instant hot pack might contain something like calcium chloride or magnesium sulfate and water. It's very exothermic. Our calcium chloride is a -80 kilojoules per mole for our delta H of solvation. And that means that it's going to get hot. It's going to release that energy to the surroundings, which then heat up. A typical instant cold pack is made with ammonium nitrate and water instead, and that's actually endothermic. There's a positive delta H of solution for that process. NaCl that we talked about has a very small positive delta H of solution, but it's small enough that you mostly wouldn't notice if you just dissolved salt in water. It wouldn't really feel just to your hand like anything was changing at all. But if you've got a thermometer at home, you can do this and see that the temperature does in fact go down. It gets colder because the system is absorbing that heat from the surroundings. Solvent interactions here are going to play a role like the hydrogen bonds that we talked about. But the biggest thing that makes the difference here is the delta H of the lattice, which is our ionic bonds that we have to break and how hard that is. So the question is, if a salt has a positive delta H of solution, that is, it's endothermic, shouldn't it be insoluble? And this is where we have some deep thinking to do. Why would an endothermic process be spontaneous? And we have to remember, of course, having a negative delta H or an exothermic process is favorable, but it's also true that having a process with a positive change in entropy is favorable. We have to consider both things when we're talking about spontaneity. So we need our equation delta G equals delta H minus T delta S. If this is a negative delta G, that means it's spontaneous. But we've got to consider the impact of our delta H and our delta S. Now, depending on whether these agree with each other or disagree with each other, that is, if they're both favorable, like a negative delta H and a positive delta S, then delta G will always be negative and it will always be spontaneous. But if they disagree with each other, like if we have a positive delta H, an endothermic reaction that's not favorable, and by enthalpy, then in order for it to be spontaneous, we need the entropy to be favorable. And we can magnify the impact of the entropy by increasing the temperature. So let's look at a couple of specific examples. Generally, whenever we're dissolving salts, because they're a solid and then they're going to dissolve in water and separate out into their ions, delta S is usually positive when we're dissolving the salts. So that's going to be favorable for us. And depending on whether our delta H is positive, an endothermic solution reaction, that would mean things tend to be more insoluble. And if delta H is negative, the compound will tend to be more soluble. But it can also depend on our temperature. Typically, a higher temperature will increase the solubility because it's that T delta S piece. If I have a favorable entropy and I raise my temperature, then this piece gets bigger and bigger and bigger. That's going to make it more negative, our delta G more negative, and make it more spontaneous. So a little question to think about here: when you dissolve a salt in water, the solution gets cold. Is the solvation process driven by enthalpy or entropy? So take a minute and answer this on your own. So here we see that the solution gets cold, and if the solution gets cold, that means it's an endothermic process. Heat is going into the system, and it takes the heat from the surroundings, which is our solution, the thermal energy available in the solution. And so if it's endothermic, then that means our enthalpy is not favorable. But if it's happening, we are able to dissolve it in the water. That means it is spontaneous. So that means our entropy must be favorable. So this solvation process would be driven by entropy. Okay, these are some of the key ideas that we talked about today. The idea that spontaneity is related to both enthalpy and entropy. We need to consider both whenever we're thinking about a process. We know that it's favorable to have an exothermic process where the products are going to be more stable than the reactants. So that helps us have a spontaneous process because a negative delta H contributes to our negative delta G. And we also know it's favorable to have a positive change in entropy, a positive delta S, and that also contributes to our negative delta G because of our minus T delta S part of the equation. And in any case where we have a positive delta S for a process, then we can magnify the impact of that by raising the temperature. Raising the temperature will increase because our T delta S are multiplied by each other. That increases that favorability due to entropy. And of course, the opposite is true. If we had a solution process where the delta S were negative, for example, if we had a gas that was dissolving in water, it would be more constrained at the end. The delta S would be negative for that process. Well, then we want to minimize the impact of entropy by lowering the temperature so that our T delta S is smaller. Okay, that's everything for this today, and I hope it's helpful, and I'll see you in class next